So last week we had introduced the topic of trees, and we pointed out how in a tree there is always one path from one node to another, and there is a designated node which is called root. And therefore we started talking about the representation of the rooted trees, and we pointed out that fundamentally, when the tree node can have any number of nodes, the most efficient representation can be storing the item in the node, and then it can have uh, the the children linked together in the form of a linked list. And therefore every node has a first child and then the next sibling link. And in this way, one can move from the first child to the next like that until hitting null, in which case it has reached the end of the list of children. And just like the data structures in the past, we had talked about properly organizing them um, in the class hierarchy. So the tree node, after the tree node has been defined, then as far as the tree itself is concerned, it just involves pointing to the root, because with respect to the root, now you can go and access any other nodes within the tree. Okay, so now why did we even bother to represent something in this tree format? What does it give us? What would be a practical example of such a thing?
A file system.
Very good. So one very obvious example would be file system. Because if you notice, the whole file and folder system, they form just like a tree. And at the leaf level in the file system, you have a bunch of files, and then any nodes which are intermediary reaching up to the leaf nodes, they are like the folders within the file system. So now, if you have a file system, what is the most basic thing that you would like to do? So when you are, let's say, learning some commands of the Linux or Unix, then what kind of commands do you generally learn? It's about switching folders, right? And when you are switching folders, all you are doing is that you are walking down this tree. So in other words, when you have a tree-like structure, whatever their application may be, then the fundamental operation that we would like to perform is walking down the tree, right? So that walking down the tree is what is called traversal. So traversal is a manner of visiting a node in a tree. But more importantly, we want to visit it only once. We don't want to visit necessarily more than once. Now, after you visit a particular node in the tree, what you do is completely up to you. For example, when you have these tree nodes stored in this kind of fashion, the node may contain some data. So like we oftentimes when we want to just show an example of a tree, we start putting down some random number here, right? So that's essentially representing some data, right? So when you have these data present within the tree, when you visit them, what could be one thing that you could do? Can you think of something? So suppose from the root node, I went to the right, and again I came to the first child, and through the linked list between the nodes, I end up in this node. Then what could be one thing that I can do after coming here? In other words, the visiting is generally associated with some operation you would like to perform upon hitting that particular node. So what could be an example of operation? Let's think about this being a file system. Okay. Suppose you are walking down the file system and you encounter a node in the file system, which could be either a file or a folder. What could you do potentially?
You could like print everything out on a given level.
Yeah. Yeah, you can print the specific name. So print can be, you can print the name, you can print the level. So you can do so many different kind of printing, correct? Or you may like to do some operation. So suppose you are wanting to just sum up the number of files and folders in the system. So as you're traversing, you may like to just accumulate the sum of the nodes that are encountered. So you may like to just keep adding them. In other words, when you are visiting, it just gives you an opportunity to perform some operation. And that is why you want to traverse. So if we take another example of a tree, so this is one example of file system. Another example could be, can you think of something apart from file system? Something you encountered in your homework that could be potentially a tree? How about if I write an expression like this? A plus B multiplied by C. Now, depending on the precedence of the operation, the tree will get organized, right? So you would like to perform multiply first. So you can draw a node. And then here, you're multiplying. You're multiplying B and C. And whatever the result is, then you are performing the add operation with A. So this kind of tree could be expression trees, right? So here also, if you have such a tree, while you are walking down the path, maybe you might want to just execute. If you know the value of B, if you know the value of C, you may start actually computing these operations. Okay. So the bottom line is that when we are traversing, we have some operation in mind because of which we are traversing. We are not just traversing for the sake of traversing, right? That's the key point. Another important point I wanted to introduce, in fact, from now onwards, you can keep this in mind, that whenever we are talking about a node, right? So far we said that, okay, node contains some item, some number, and so on and so forth. So typically a node can be just a structure, right? It's a structure, meaning it's a collection structure or a class. So typically the class as we define, it's just collection of data, right? Now out of this collection of data, you can think of, there would be certain element within that collection that would be something very special. For example, suppose I am storing in these nodes the attributes of a student. Okay. So suppose I'm interested. So every node is representing a student. Okay. This is say another example. So every node is representing a student, and every node has got varieties of attributes of a student. So what kind of attributes? Can be name, can be ID. What else? Maybe year, department. So there can be so many attributes that can be associated with a student. Now, when I am looking for something, right? I may like to look for something which is very unique, right? In order to identify a student. So there may be multiple students with the same name. So name may not be uniquely identifying a student. But definitely a lot of effort would have gone into the university system to make sure that no two students have the same ID. So this could be a candidate where you can uniquely identify a student. And likewise, you can see year and department, they don't uniquely identify a student. So once you have such an attribute or such an element within this collection of data, that designated element which can uniquely identify a particular node, that can be referred to as a key. In other words, key is something that you use to locate a node. So key, so here ID could be a key. Key is used to locate a node. Locate or identify a node. And the rest of the attributes, right? They are just like various values. Okay. So from now onwards, without any reason for us to discuss these details, what could be stored in a node, because that can be variegated depending on the nature of application, depending on what you are dealing with, it can vary. But what is most important to keep in mind is that there must be something which can be identified as a unique key for the node. Okay. So there would be a notion of key, and the rest would be kind of the notion of value. So we can say a node typically has a key and value, and you can see it as a singular or you can see it as a plural. It does not matter. But from now onwards, whenever we are talking about creation of a node, think of a constructor which is passed in. The constructor will receive a key and a value minimally in order to construct the node. Any question on that point? Is that clear? Okay, so if you get that clarity, now let's talk about what are the different ways you can traverse a tree. Okay, so traversals. The first kind of traversal is called a pre-order traversal. So what is a pre-order traversal? So you visit each node before recursively visiting its children. And generally, conventionally, the visit is from left to right. Now, if one is going from right to left, That means the linked list also should have been organized that way. But in this case, left to right essentially means in the direction of the, the organization of the list for the children. And of course, you visit, so root node is visited first. Okay. So if we were to write a traversal routine, so let's say you had the class, the tree node class, right? So you had the tree node class. So above, you had the tree node class, right? So I'm writing a function here, which is void pre-order. So which means that you are starting the pre-order traversal starting from this node, you know. So that is essentially the root node with respect to the client, whatever has been passing in, or not passing in, whatever is calling the pre-order function, with respect to that pre-order function, this node is the starting point, and therefore is the root of that subtree. So the basic idea of pre-order is that when you have certain nodes here, the basic idea is that you're visiting the node before its children. So because you want to do the visit of itself first, therefore the first thing that you do is you call visit. And this visit essentially means, as I mentioned before, it can mean any action. It can be, for example, the print action. So if I have stored 5 here, right, this may mean just see out the corresponding key or value, whatever it is, you're performing corresponding to this action, visit. Okay. So whenever I use the term visit, it essentially means you perform some operation associated with that node. Okay. After performing the operation, then I start visiting the children recursively. And how do I recursively visit the children? So you check first if first child is not equal to null, then you call first child and you call pre-order on that. And then after that, you visit all the sibling nodes. So next sibling not equal to null, then next sibling pre-order. Okay. And that's about it. So you can see that that this naturally would lead to visiting all the subsequent nodes from here. But maintaining this whole idea that I want to visit first the leftmost child, and then you correspondingly visit the subsequent children. It's as simple as that. Any question on the pre-order?
Wait, so what does a visit function actually like do though? Why can't it be like any action? Because like
I'm saying
yeah, could you
it is
a bit more about that?
it is going to be any action. This is like a generic way of saying any action. I'm just introducing a nomenclature here. And the nomenclature is that whenever you see the word visit, that's why I was explaining before, you visit for a reason. You don't just visit for the sake of a visit, right? So visiting corresponds to performing some operation. So here, if you have certain application like printing every single node, right? So instead of visit, what you're going to put here, you're going to just say cout less than less than. Now this is this node, right? This is the current node. So current node, you may like to print the key. So you may call key less than and L. So this would represent essentially visit. This would be an example of performing the visit. Is that clear?
Yeah, that's clear. Thank you.
Yeah. So that's why in the beginning, I just want to make sure that you understand this whole notion of key and value, and you understand what visiting entails. So visiting means performing some operation. Okay.
Pardon me, would you use the same structure if you're doing a search? So instead of visit, it would be the base case of matching something?
So when you are searching, right? So this visit will amount to what? You would be checking the content of this node against the value, right? That's what you mean, correct?
Yes.
Exactly right.
Thank you.
So depending on the operation, what you're going to do pertaining to that node is going to vary. And that's going to be very contextual. And therefore this visit word is just capturing in the most general way that you do something when you are reaching that node. And what you do, it's completely up to you. Because what we are giving you here is just different ways you can visit these nodes, the strategies of visiting these nodes, or the order in which you may visit these nodes could vary. So you may like to print something, but you may like to print something in a particular order. So if you want to print something in a way that you want to always print the parents attributes before the children's attributes, then the pre-order traversal is perfect for you. Does that make sense? Is that okay? All right. So now what would be the complexity of this? So from now onwards, we're going to ask ourselves this question. So what would be the time complexity of this? So when we are asking for time complexity, in most cases, the variables that we are dealing with here is the number of nodes, right? In the context of tree. So let that be n. If there are n nodes, what would be the complexity of this algorithm? How many times are you visiting every node here? Using this algorithm, how many times are we visiting every node?
N
Once.
factorial.
So here you see that there is no way we can visit the same node twice, right? Because we first define a tree given any two nodes, there is only one path, right? From one node to another. And here you are starting from the root node and then you are subsequently visiting every other node. And because there is only one path, right? Therefore, you're going to visit every node only once, correct? Any question on that point? So in other words, you're going to call the visit or performing some action. You're getting the opportunity to do that exactly once, right? So each node is visited exactly once. And that's the basic reasoning why the time complexity is going to be order of n. Okay. So post order is just opposite of pre-order. So post order, you visit the current node last. So this would amount to essentially the same kind of code. It's just the visit will be placed after the recursion that is going on. And it's going to be as simple as that. Okay. There is one more kind of traversal called in order traversal. That is undefined for trees of trees where a node can have more than 2 children. So this is particularly relevant when we are discussing binary tree. Okay, so we'll come back to that now. Any question? So these are the basic ways you can traverse a tree. Now, of course, there is another way of traversal, which is called level order traversal, which we'll get to when we are discussing graphs. At that time, the level order traversal will get discussed in the form of what is called breadth first search. So at that time, when we study this, you can understand that the same principle can also be applied to the trees. But I don't think we need to go into this today. Any question? Because we are going to switch gear to now talk about binary search trees.